right, hello ladies. Today we are going to be starting a new chapter, and this chapter is kind of a continuation on the previous, still talking about different functions and relations and things like that, but instead of talking about polynomial functions, we're going to be talking about exponential and logarithmic. So this unit is a little bit going to be split up into two parts. 8.1, 2, and 3 is all going to be about exponential functions, and then 8.4, 5, and 6 is all going to be about logarithmic. The reason that we pair them together is that they have some key similarities that we'll kind of analyze as we go through the unit. But for now, we are just going to introduce exponential functions. With that, what you will need is you'll need your Desmos app at the ready, because we're going to be graphing some stuff via Desmos. And then we're going to be copying those graphs down below. Okay? Alrighty, so an exponential function is a function of the form y is equal to a times b to the power of x. I'm going to make this a little bit thicker. That seems too thick. Oh, bye-bye. So now we have our variable in the place of the exponent. It's not the base, it's not the coefficient. A, in fact, is our coefficient. B is our base. And X is our exponent. You're right, that was too thick. Poor choices were made. Alright. Couple of restrictions. A has to be greater than 0. Okay. And B has to be greater than 0, and B cannot equal 1. Right? Because if B is equal to 1, B is the base of our power. And 1 to the power of anything is just 1. And A, our coefficient, times 1 is just going to be itself. And so if B was equal to 1, our graph would look like y is equal to a, which wouldn't give us an exponential. It would just give us some horizontal line thingaling. So, that's a no-go. So those are some restrictions that we have. Alright, what we're going to be doing is on our Desmos, we are going to be graphing the following. I'm going to zoom in a little bit here. And we're just going to see what our graph looks like. So, we have y is equal to 1 times 5 to the power of x. Note, to get to the power of something other than 2, you have to hit a to the power of b and then hit x. That goes into the exponent there. And this is what our graph looks like. So if you see, it goes and starts all the way from the left-hand side of the page and then skyrockets as it hits the right-hand side. We have a y-intercept of 0, 1. So we'll draw that in. And you know what? Why don't we label that 2? And just for fun, we want to graph a few other points. So why don't we say what happens at x is -1 and what happens when x is +1. Just to kind of get a sense of where those points are. So, when x is -1, our y is 0.2. So like 1/5 of the way up. And when x is equal to 1, we have y is equal to 5. So that's our point there. And just for the sake of taking a peek at these, -1, 0.2, we'll graph them as such. Now, as we can see in our Desmos, our graph continues on forever. It continues on and on and on up to the top. Well, if we look to the left, we want to see, well, do you think it'll ever hit the x-axis? And as we continue on further and further and further to the left, you could keep on going forever, zooming in more and more and more and more. You'll actually find out that it never does. Exponential functions will not have an x-intercept, as they will never reach that x-axis. So what we're going to do is we are going to draw this as best as we can to resemble what we have on Desmos. From here it goes upward. And if it doesn't look perfect, I totally recommend doing this in pencil, so that if it doesn't look great, you can erase and try again. Especially when we get to drawing the part of the line that gets really close to the x-axis, because you don't want to cross, because our graph never does. Okay. And that's what we have. And we're going to draw arrows on either side of our function to make sure that it indicates it goes on forever. A couple of other things is we want to make sure that we indicate our scale, right? We're going up by 1. And so that we know every box indicates 1. And we also want to indicate our x and our y-axis just to have an appropriate graph here. Okay. We're going to be talking about our domain a little bit. We're going to be talking about our range, and so on and so forth, and answering a few questions about this graph itself. So our domain, that's our whole interval of x. We can see that from the furthest to the left, it continues on to negative infinity, and going to the right, it will continue on to positive infinity. I know that you can see that it's going upward, but it's not going directly upward. Even though it looks like it's going up at a pretty steep rate, it is inching over further and further and further to the right, and over time we will see that eventually hit positive infinity. For our range, okay, like I mentioned, our graph never hits our x-axis. You can scroll over on Desmos and try and find a point in which that occurs, but you never will. So, our range is essentially 0, but it never includes 0. So our range will have a soft bracket there. And our range going up as high as we possibly can will go up to positive infinity. Okay? Since our range does not include 0, that means we're never going to have an x-intercept. So we have 0 x-intercepts. And for when we say what is that x-intercept, we often write DNE because that's the abbreviation for does not exist. Note that you can't just put like a 0 here because that implies the x-intercept occurs at x is equal to 0. So that would be incorrect. But you can put DNE as in it does not exist. For our y-intercept, we can see that there's one of them. And that actually occurs when y is equal to 1. When writing your y-intercept, you could either write it as y equals to 1, or you could write it as the coordinate point, so that point 0, 1, because we always know that y-intercepts occur when our x value is 0. And for our end behavior, we are going from our quadrant 2 all the way to our quadrant 1, right? Because since it never reaches that x-axis, it will not cross over to quadrant 3. So for our exponential, we have the end behavior of Q2 to Q1. And turning points, we can see that as we move from left to right across the graph, it is always increasing. It never changes direction, so we have 0 turning points. Alrighty. Next guy here, we have essentially the same graph, but instead of an a value of 1, we have an a value of 4. So let's just pop that in. When we graph this here, we want to find out what some of these points are. Of course, on our graph, it doesn't continue on as Desmos does, but I'm going to indicate my scale, so it's going up by 1. I'm going to indicate my x-axis, my y-axis, and then we're going to start plotting some points. So my y-intercept, I can see very clearly, is 0, 4. So 0, 4. And when x is negative 1, I could see it's at 0.8. And x is 1, when x is 1, we have 20. So it's way up there. Okay. we are going to go ahead and try and replicate what this kind of looks like here. So it goes up pretty quickly. Oops. And like I said, you want to use a pencil because if it doesn't look right, you want to be able to redo it. Okay. And going the other direction, it curves off pretty quick and continues down that way. Of course, your graph may not look perfect, and no graph ever will, but you want to do what you can to replicate what that looks like in the space provided. I'm also going to indicate this point here, -1, 0.8. And, of course, we have some point way up here, right, if we want to continue, or at least have an idea of where that went on to. You're more than welcome to kind of draw that as a reference point, but it's not mandatory, because it's not on our graph. For our domain, same idea. Let's go to some really low value. Why don't we say our x-axis goes all the way down to, I don't know, some really big number. And if we zoom in, I'm going to artificially zoom in here. And let's say I zoomed in too far for Desmos to handle. And zoom in, zoom in, zoom in, zoom in, zoom in, zoom in, zoom in. See if it actually crossed. We can't zoom in any more than what we already are. And we are getting to ridiculously small intervals, and we could see that it still hasn't touched, right? Because if it touched, we would be able to see some sort of point and where it intersects, and that does not exist. Okay. So our domain continues on from -infinity all the way to +infinity. Our range, just like before, is 0 to +infinity because that 0 is not included. It's a soft bracket. We have 0 x-intercepts that occur. And what is that x-intercept? Well, like I said, it does not exist. We have 1 y-intercept, and that y-intercept occurs at y is equal to 4. Or you could say 0, 4. The end behavior, just like before, was Q2 to Q1. And there are 0 turning points. Just taking a peek here at these two graphs and the numbers of their equations, there might be a couple of things that you've noticed. Oh, first of all, that's an ugly color. This is what I wanted. For starters, our A value of 1, here you might have noticed that we have a y-intercept of 1. Our A value of 4, you might have noticed that we also have a y-intercept of 4, which is kind of neat. Okay. Another thing that maybe you did or maybe you didn't notice, this one's a little bit more tricky to notice, is that for this point here, when x is equal to -1, our y is our A value divided by our B value, right? 1 divided by 5 is 1/5, or 0.20. And our point when x is equal to 1, our y is A times B. 1 times 5 is 5. Same thing here. So when x is -1, y is A divided by B. 5 divided by 4 gives us 0.8. And when x is equal to +1, our y is A times B, which is 4 times 5, which is 20. And if we're looking at Desmos here, that's the point we have. So there might be a couple of interesting points that you might have realized from this, but most importantly is that A value. The A value really determines where that y-intercept occurs. Cool? Alrighty. We are going to look at 2 more graphs, but this time we're going to look at what happens when our b value is a fraction or a smaller value. What I will get you to do, I think I did in your notes, but I didn't do here, is I would like to change our second question to y is equal to 3 times 0.75 to the power of x. Okay. All right, so for this one here, we have a of 2, or b is 0.5 to the power of x. Before we even graphed on Desmos here, we should know what that x-intercept is going to be, where that's going to happen. And because our a value is 2, our y-intercept should occur at 2. So we should be able to graph that with some decent confidence right from the get-go. And we're going to plug this in and verify everything else as well. 0.5 to the power of x. And here we go, 0, 2, just like we imagined. What we were talking about on the previous page, before we even just look at Desmos here, we said when x was equal to -1, our y value was the same as a divided by b. So 2 divided by 0.5, which is positive 4. And check that out. There we are. So that's kind of cool that that pattern exists. So when x is -1, we have a positive 4. And we also know from the kind of pattern that we've seen on the other side, when x is positive 1, y is our a times our b value. 2 times a half is actually going to be plus 1. And there we go. We have the 0.11. So that's kind of cool. Again, we don't have to estimate our points because we have Desmos there, but just kind of cool to recognize patterns when they exist. I know that's always neat. So we're going to go ahead and we're going to draw our curve. It continues on upwards in this direction, and it continues on. And if we look at our Desmos, same idea, it will never touch that x-axis. Whoops. So when we're looking at our domain, that's our x values from left to right. So we have negative infinity all the way to positive infinity. Our range, same thing. We started from the bottom and we're going up, bottoms up. Our range, our lowest value is 0. Our 0 is not included because it never touches our x-axis, and it goes all the way up to positive infinity. How many x-intercepts we have? Oh, that's a silly question. We have none. And what x-intercept is that? Well, it doesn't exist. Our y-intercept, we know that occurs when our whatever a value is. So y is 2, or we could write it as 0, 2. Oh, I wrote that in the wrong spot, you silly goose. All right, so we have one y-intercept, and that occurs at y is equal to 2, 0, 2. Our end behavior, same thing. If we're moving left to right, that goes Q2 to Q1. And how many turning points? It is always decreasing. The graph is always going downwards, and it doesn't change, so we have 0 turning points. Last but not least, we have one more graph to take a peek at, and that is y is equal to 3 times 0.75 to the power of x. We can go ahead and start imagining where some of these points will exist before we even use Desmos for all of its powers. We know that the a value represents the y-intercept, so we will have a y-intercept at 3, so 0, 3. We know that when x is -1, y is our a divided by b, so 3 divided by 0.75. If you're doing some quick math in your head, that's 4. So we should have a point here at -1, 4. And when x is equal to +1, our y is equal to a times our b. 3 times 0.75 should be 2.25, so somewhere-ish in that neighborhood. Oh, that's 1.25. Silly me. 2.25. Somewhere around there. 1, 2.25. And there we have it. So we could graph on Desmos, obviously, to make sure we're correct. Again, you will always be provided Desmos. It's not something that I'm going to take away from you. So you could use that to your discretion. But just to kind of confirm that we got the same point, it's always neat to kind of see the pattern. All right. We could continue on, kind of connect the dots as we go, draw in a nice curve. Okay, so we get that nice curve. On both of our graphs here, we want to make sure that we have our scale, our X, and our Y axes labeled, just to make sure we're doing our due diligence here. All right, for our domain, same as before, negative infinity to positive infinity. Our range, again, same as before, 0 to positive infinity. How many x-intercepts? Oh, we have none, which means they do not exist. For our y-intercept, we know that occurs at our a value, where a value is 3, so that occurs, I'm getting ahead of myself. We have one y-intercept that occurs at y is equal to 3, or 0, 3. Our end behavior, as it moves left to right across the graph, we go Q2 to Q1, right? Because since it never crosses the x-axis, it never reaches quadrant 4, so it ends off in quadrant 1. And it's always decreasing. We have 0 turning points. So now some questions. What can our A and B values tell us about the graphs? Okay. And so we've kind of discussed this a little bit, but we're going to discuss it a little bit more. For our A value, we notice that our A value actually tells us what that y-intercept is. So the A value determines the y-intercept. And that occurs when y is equal to whatever that A value is, or at 0, A, that point. Now the B value, that's a little bit different, okay? What you might notice about our first two graphs is that they were both increasing, and the second two graphs, both of them were decreasing. Why do you think that is? Well, we know B always has to be greater than 0. B can't equal to 0. But what might be interesting to know is that when B is greater than 1, the function is increasing. So on our first two graphs, we had a B value of 5. And both those times, our graphs went and increased as we moved across left to right. When B is greater than 0, but it's smaller than 1, the function is decreasing. So just by looking at the equation of the graph, and without graphing it at all, we can see a couple of key pieces. We can see that the y-intercept occurs at that A value, and we can tell if it's increasing or decreasing. And just knowing those little bits of information can be helpful when we're looking at our answers. Do they make sense for the situation we're given? Or if we're trying to match up equations to graphs or things like that. Okay? So something kind of cool to think about. The last thing that we are going to do is we're going to just make a general kind of cheat sheet here when we're talking about exponential functions. Okay, so I'm going to put Desmos away here. I'm going to try to. So, when we're talking about any exponential function, you probably might have noticed a pattern. And when I say any exponential function, I talk about things not in terms of word problems, right? Because with word problems themselves, we have different limitations that exist and are introduced with each question. So we can't say this is going to be true for every word problem, but we could say it's going to be true for every graph. Our domain will always be from negative infinity to positive infinity. Or x values can be anything. Our range is always going to be from 0 to positive infinity. Because we'll never actually hit the x-axis, right? So we could be anything greater than 0, but not equal to 0. And that's why we use a soft bracket. We will always have 0 x-intercepts because we cannot have that value, which means the x-intercepts do not exist. We will always have one y-intercept, and that will always occur when y is our a value, or at the point 0, a. And our end behavior is always going to be from Q2 to Q1, quadrant 2 to quadrant 1. Okay? And we will always have 0 turning points. The one other thing that we know is that if b is greater than 1, the function will be increasing. So in general, the graph is going to look something like that. And if b is less than 1, but still greater than 0, because what we saw in our original restrictions is that b had to be greater than 0, and b cannot equal to 1, is that we will see a graph that is decreasing. So it'll start up here, and and slowly go down. Notice on either side these arrows that are getting really, really close to the x-axis as they continue on will never touch. They are approaching it. Okay. So what we say is that there's a horizontal asymptote at y is equal to 0. So a little bit of what that means, or what that looks like, is if we have a graph. You know what? I could draw a straight line. I forgot about that. Okay. We have a graph. Well, let's draw some scale. 1. Y equals 0 is the line that occurs right on that x-axis, right? Y is 0 on any point on that x-axis. So we say there is a horizontal asymptote at y is equal to 0. What an asymptote is, because you might hear that word every now and again. An asymptote is an imaginary boundary line that exists in which a curve approaches. Curve approaches but never touches at any value. Okay, so that's an actual definition of an asymptote. But the way you can think about it, if you don't want to think about it in terms of the actual definition, is when we have some sort of graph, think of that asymptote, that green line, as an electric fence. If we touch that electric fence, we get electrocuted, and boy, does that hurt. So we're not going to touch it. But we're feeling a little ballsy. Why do we want to get as close as possible? Just to play with fire a little bit. So that asymptote exists as in you can't touch me, you can't cross me. But the curve being a little bit on the ballsy side is just saying I'm going to get as close as I can without actually touching. And so that asymptote exists as that fence, and the curve exists and says I get really, really close, but I can't touch you. Okay? At any value. So no matter how far you go this way down the graph, x can be 18 billion but it will never actually touch that asymptote where y is equal to 0. And this is true. There's a horizontal asymptote for every single exponential function that's graphed. Okay. All right, so we've just introduced exponential functions, nothing too crazy. There's a little bit of homework for you to complete. Again, nothing too crazy, just a page. The answer keys are posted online, so once you're ready, check your answers. And I hope you have a wonderful day. Adios, muchachos!